article, and there are very good examples of functions of two variables among many other applications if you're thinking about weather, because, for example, if you could lay out a map of the world, and then you could have satellite data, say, that would record wind speed for a pair of coordinates on the map. So your coordinates, where are you on the map, would be the variables, and then the wind speed would be the function value. So that's a similar example. It's pretty easy to understand as a concept, I'd say.
Thank you.
And so if you look at the formula, well, first of all, if you look at the data that's in the newspaper article, you have the actual air temperature that you'd measure, say, on a thermometer. And the thermometer reading would be independent of the wind speed. But what you would feel then would be the number that's in the body of the table, and then you have your wind speed in the newspaper article on the vertical in the darker color there. So for example, where I drew the lines, we're talking about a wind speed, say, of 15 miles an hour, and a thermometer reading of minus 15, and you see the number. I think that that's probably colder than it actually does feel, and that's why they're saying it should be revised. I was in the Korean War, and in North Korea, there was a place where I was where the thermometer reading was about minus 20 in Fahrenheit. Artillery pieces have thermometers with them because what amount of charge you need if you're going to fire the thing is temperature related. So that's something that kind of comes with the thing. So there was plenty of capability to determine the temperature on a thermometer. What the real wind speed was, I'm less sure of, but people were saying it was about a 20-mile-an-hour wind. So 20-mile-an-hour wind and 20 below zero. Well, it's life-threatening, obviously. I mean, about all you can do is try and live. So anyway, this is an example that I have some feel for, shall we say. Now, if you're looking at maple, say you look at the other sheet of paper, this is the formula that produces the numbers that are in the newspaper article if you round off the readings. So W then is your wind chill, so that would be the number that's in the body of the table of data. And the V would be the velocity, and the capital T is the thermometer temperature. And these numbers are based on experiment by whoever originally cooked this formula up. Just a second here and we'll continue.
So is this the convective heat transfer formula that we circulated?
I really don't know how they came up with the coefficients. What it's supposed to do is give you a number that is what you would feel if the air were not moving. Okay. just exactly what assumptions anybody made to get the numbers, I honestly don't know. And so anyway, they have these numbers. So if you're, what I'm trying to talk about here is how you would use Maple to enter a formula for a function of two variables, regardless of how the formula is derived, and then how you would interpret the graph. What we're after here, really, as far as the mathematics, is that the graph is going to be some kind of surface. So you have your colon equal, so you're defining this function by the name capital W, and then your variables, and then you make the arrow, so that's the minus sign and the angle bracket on the bottom of the keyboard. And then you put in your numbers, whatever they are, as a formula. Remember, SQRT is square root. So it involves the square root of the wind speed and in the one term, and then this decimal times the wind speed. Then all of that is times the number minus the temperature. Okay, so Formula 1 then, Maple understands that W is this function that's there. So then if you want to get the graph, you see plot 3D if it's a surface. And you use plot if you have defined your formula as a function. We'll talk about that in a minute. So plot 3D, the function that you've just defined, and you see it's two variables. There's V first and then T. So if you want a surface, you need limits from and to for each of your variables. So this is saying that V is greater than or equal to 5 and less than or equal to 30. And it's saying that T is greater than or equal to 0. And, it's 0 is greater than or equal to T is greater than minus 25, say. And then you have different styles you can name for surfaces, so you can see what patch contour is by having chosen it. Boxed axes, they could have been normal axes, tidal, whatever you want. So you see then on the vertical, the numbers are your temperatures, where the 0 would be clear at the top, the way that I had entered the numbers, 0 to minus 25. And then you see the wind speeds, or rather the let's see what, you see I have the wind speeds across the bottom there, and I have the temperatures. Let's see, which way am I going now? No, I have the wind speeds across the bottom, if you're holding up the paper, from your right out over to the corner at your left. So there's your 5 to 30. And then the temperatures across the bottom from your left hand, if you're holding the paper like this, down diagonally toward the right. And that's the minus 25 to 0. And then the wind chill, what's supposed to be the equivalent reading in still air, would be all of those negative numbers. So if you want to, then if you turn the page, You can also do plot and have the axes normal, so that's the picture on the top of the back page instead of boxed. And so you see an origin. And then if you want to see the values for a particular temperature and various wind speeds, you could do EVALF, which is floating point, which is decimals. Then the map is to give you a whole, map is the command that produces a function table. So it's producing the function table values for the wind speeds 5 through 30 miles an hour at -10. And you see you get these decimal numbers, but if you round the numbers off, then they're consistent with what's in your newspaper article. And so I have for -10, that's line 2, or for -15, that's line 3, or for -20, that's line 4, and then the numbers. So this is how you produce the graph and compute the values for a function of two variables based on a formula. And so if you're trying to use Maple, this would be a guide of how to get a function of two variables into it. So you have, first of all, two ways to interpret a curve in a plane, and then we're going from there to two ways to interpret a surface, which is really what this chapter is about. So if you were thinking of a curve, first of all, you could consider it as the graph of a function of one variable, and you'd use plot if you were getting Maple to do it. Or you can think of it as what we will be learning to call a level curve defined by an equation. So instead of, if you were thinking of the graph defined by this equation, that's a circle, is the center at the origin, radius 1. And the corresponding approach as a function, then, you'd have to take, say, solve for y, and you'd have to take the positive square root for the top half and the negative square root for the bottom half. So if you did that, then you'd use the command plot in Maple. And if you're doing it with the equation, what you would have then is implicit plot. And then if it's implicit plot, you have to say x equal somewhere to somewhere, and then comma, and then y equal somewhere to somewhere. So if you were looking at something like this now, you have a function of two variables, and the z then would be, for example, your height up to a surface. So if you were thinking of a particular height that you chose, such as, for example, if you were looking at this as a level curve for this graph, you'd be looking at x squared plus y squared equal 1. So then this would become 6 minus 1 and would give you z equals square root 5. So the circle in the xy plane with radius 1, you can interpret as a level curve, meaning that if you're going around that circle, your z values are always square root of 5. So what's level is that your intersection in a sketch like this would always be at the same height. So you'd have a situation like this. You see your z equals square root of 6 minus x squared minus y squared is going to be the top half of the sphere. And then you have, say, a vertical axis. You have your level curve down here. That's your unit circle. And then as you come up from it, you have all of these points at square root, at height square root of 5. So you'd call this circle down here with radius 1 a level curve in the sense that for each x, y that's on it, the height to your surface is figured this way, and so the intersection up here with the plane z equals this number is it's the intersection of the surface with a plane that's parallel to the xy plane. That's what's level about it. So you can interpret this curve down here in the xy plane as a level curve for some surface, and then graph it with implicit plot, or you can solve for y as a function and draw the 1/2 of the circle with the positive square root and the other with the negative square root. So you can always interpret a curve in the plane in these two ways. Now you can do the same kind of thing if you have a three-dimensional surface. So again, looking at this same example, you can look at the blue surface now in two ways. You can look at it as a function of these two variables, say this function, and that gets you now the surface. Like that. And you'd recognize that as a, well, what I've drawn is a quarter of a hemisphere, but it would go on around. So you can write your surface as a function then of two variables like this, and use the command plot 3D if it's Maple. Or you can think of the related implicit plot situation. Say you squared both sides, so you'd have this and then that. And looking at it this way, you see this is a graph of a sphere centered at the origin, radius square root 6, and you call that a level surface in the same way that you would have called the orange in this picture a level curve. And so it would be a function of the three variables, w of x, y, z, equals some constant, the same way that this was a function of two variables equal to some constant. Another word that people use for a level surface is the word isotimic. Iso is Greek for same, like isosceles triangle, or two sides the same. Or isothermal is same temperature and thermodynamics. Isobar is same pressure and weather, say. And then timic, you can see time. So if you're looking at your function of three variables like this, for which the graph would be a sphere when you choose a particular value for W, we're saying at all points on that sphere you have the same value for whatever W measures. So they could be temperatures with some source of heat at the origin, or they could be electric potential or something like that. So in maple graphing, for functions you're going to use plot if it's like this, which would be, say, the top would be half of my orange circle, or plot 3D if you're going to use this and draw, say, the top half of the sphere or part of that. And for relations, either the contour like this in your contour map, or your surfaces as level surfaces, you're going to use implicit plot or implicit plot 3D. So you could have the concepts for more than three variables, but you can't really draw them, so we don't go there. But our book does go with things that I've described here, either surfaces as functions of two variables using plot like we did with the wind chill, or surfaces as a function of three variables equals a constant, where it's like it's the equivalent then of your contour. Just a minute, I gotta drink some water. If you want to write a function of two variables, like problem 1, say in the book, you notice this is a much simpler function to deal with than the wind chill function. You can give it a name, such as f, okay. Then your colon equal is defining a function named f. So then, again, if it's two variables, parentheses x comma y. If it were three variables, like problem 4, you see it's x, y, z. And then the arrow, again, the minus sign and the angle bracket, and then your formula. So with problem 1, you see it's x squared plus xy cubed, and then that prints. And then you can ask for function values. Again, now it's two variables, so you have to put in your choice for x and for y. So that's 0 at the origin, and you see how you can produce whatever list of numbers you might want. In the problems, they're asking you, they give you, for example, that function and ask you for some function values. And of course, you could actually just do the problem 1 in your head easier than you could ever fire up a computer and type it all out, needless to say. But if it were a thing like this wind chill formula, that's another story. You really don't want to do that in your head. And you see the next one is very similar to my example here, the 49 minus x squared minus y squared minus z squared. So you can get function values again in the same way. Now, if you look at the exercises 31 through 36 in the book, you see that what they are trying to do there, you can look through the maple and see how these things look. Or if you have your book, you can see what's given there in the book. And what they're doing, they have a list of A, B, C, D, and so on, of contour maps in the book. And then they have a list of the surfaces, the graphs of the surfaces. And what they want you to do is figure out what contour map goes with what surface. For example, a simpler example of these problems would be something like this again. If you had a hemisphere as your surface, the corresponding contour map would be concentric circles down here in the XY plane. And you see the circle that is squeezed down to a point would correspond to the North Pole here. And as you go out toward the equator, using language that's comes from living on the Earth, of course, you see that you have a contour with an ever larger radius. So to the extent that the Earth is a sphere, which isn't quite true, the circumference around the equator would be where the belt is, so to speak. And so what I've done is use maple and kind of work backwards with these problems rather than looking at the graph like the top one on the page of problem 31F. You see the function is y squared minus y fourth minus x squared. And so if you define the function, you can draw its graph. And so that's the plot 3D style patch contour. And so you see the graph of the surface and you see the contours are put on it. And then with those contours on the surface, if you pair it with the one with the choice in the contours maps, you can see how the contours on the surface can really match with those in contour plot for the same function. So 31F goes with that picture with those contours. And then 32, I've drawn the graph of 32 on the top of the next page. And then I've done the contour plot, and that would be choice E in the choices as they're given in the book. In the book, you have the pictures, A, B, C, D, E, and so on, and you have the contours. And so I'm using maple to match the graph and the contour by asking maple to draw the graphs of the contours. So what they're trying, you can see what they're trying to put across is how if you become adept at this sort of thing, you can look at contours and have a feel for what kind of surface it is. It's easy enough to get maple to draw the surface and draw the contours for you. It's not so easy to just look at contours and be able to picture this surface in your mind. And I don't expect you to, but I want you to study through the correlation that is there if you can see it. Okay, so then, another handout. I guess I've got it here. Finally, we can do something, so to speak. So, let's see. I mean to have given everybody 14.2. Now, did I give out 14.2 or have I given you 14.1 again?
I got 14.
You
Yeah.
have. There was a 14.1 that got in with this file, but I guess it was the next one, and so I got away with that one. Okay, so let's talk about limits then. The rest of what's 14.2 is about is limits and doing limits of functions of 2 or 3 variables. So what we have, you see, with a limit in 2 variables is something that you, well, you do encounter the concept of a path-dependent limit in Math 170, but only just barely, because in Math 170, the only choice you have on a path is the x-axis. Say you're thinking of a function of x, and limit as x goes to 0 or somewhere. The only choice then is coming from the right or coming from the left, right-hand side limits and left-hand side limits. And sometimes those are different, say as you go into 0, and then you can have a right-hand limit that's one number and a left-hand side limit that's another, and then the two-sided limit doesn't exist at 0. For example, if you think of absolute value x over x, that's +1 if x is positive, and it's -1 if x is negative. Your right-hand side limit's 1, your left-hand side limit's -1, the two-sided limit at 0 doesn't exist. Okay, but that's about all that you do in Math 170 with the concept of a limit that depends on a path. But you see, if you're in a plane, so you're thinking a function of 2 variables, you're not limited to coming in to the origin, let's say, on the x-axis. You could come in on the y-axis. You can come in on a line through the origin at any angle. The line y equals x, and it doesn't have to be a line. You could come in on a curve that goes to the origin, like sine x or x squared or square root. Literally infinitely many choices now. So to say that there is a limit at the origin means that every path you could imagine has to produce the same answer. Well, you can't check all of infinitely many choices, of course, but what you can often do, and that's what's in the homework, is prove there's no limit by finding 2 paths that give you different answers. The same as in Math 170, you can prove the limit of absolute value x over x does not exist, because coming from the right gives you +1, coming from the left gives you -1. So that's where we're going with this. Okay, so that's essentially what I've said here in the writing. So now look at an example. So some of these examples are in the 14.2 handout. So, in your 14.2 handout, on the first page, about 2/3 of the way down, says examples. This first one is from the Stewart text. So, x squared over x squared plus y squared. And so, suppose you came in to the origin on the path x equals 0. Okay, that's the y-axis, isn't it, when x is 0. And so, if you if you've made this choice of path, then you've used your x when you specify this path. So then the remaining variable to come into 0 is y. So you're talking about the limit of this as y goes to 0 when you have chosen x equals 0 as your path. So first thing, you use your choice. If x is 0, you put 0 there, and you put 0 there. So now you have the limit of what this gives you, which is 0. So your answer is the limit as y goes to 0 of 0, which is certainly, you see what I've done. I've replaced the x with 0, and then I do legal algebra before I take the next limit. Well, y squared into 0 is 0, so then I take the limit of 0 as y goes to 0, and that's 0. Okay, now, here's another path. This time y is 0, so your path is the x-axis. So first you replace y with 0 in the original, and now do legal algebra, and so you have 1. So now you want the limit as x goes to 0 of 1. The limit of a constant is that constant. So you have different answers. So you don't have a limit at 0. Suppose, here's the third answer. Suppose you came in on the path y equals x. So look at the limit again on this path. So now the first step is to use your path to change from 2 variables to 1. So if y is x, replace the y squared with x squared. Do your legal algebra. So now you're talking the limit of 1/2 as x goes to 0, and that would be 1/2. So here's 3 paths and 3 answers. If you have these problems like this where there isn't any limit, what is going to happen is you can choose as many paths as you're willing to sit still for and get that many answers as a rule. So you could come in on the path kx, k is any real number really, and make your replacement, and you have 1 over 1 plus k squared, and that limit then will be whatever is your choice of k. And so you can see how you can produce all sorts of answers. So this is the game in these problems where you're given what starts out as a 0 over 0 type situation, and you're asked to decide either that there is no limit or that there is one. So if you look at your maple pictures in this 14.2 handout, go to number 41. So this is line 29 on second sheet of paper. And you see what I did first is draw the graph, plot 3D, the function, and so you have two variables, so you have to choose limits on your two variables. And you can do whatever you want with the contours on the surface or not, normal axes are boxed and title or not. Well, notice that you have this graph and then you have a big white patch in the center of the picture. That's a way that Maple is going to tell you in a picture that you're not going to, that you have a discontinuity at the origin, that you're not going to get a limit. Because what happens is that trying to draw the graph, when you get in close to where you don't have a limit, Maple can't compute a function value, so your paper doesn't get colored. So that's the white paper showing through the hole in the surface, so to speak. So this is kind of the Maple version of a black hole, say, in astronomy, something like that, where you're not going to go there twice. So anyway, the picture warns you that this is going to be a situation like we studied here in the example from Stewart. So here's our formula. Suppose you took the path where x is 0. So that again would be the y-axis. So if you're using x equals 0, you replace x with 0, and so you have 0 over y, really, and you do your division, so that's 0, your limit of 0. As y approaches 0, it would be 0. However, take the path where y is 0. So now your variable will be x. And your limit where y is 0 as x approaches 0. You see, I've replaced the y with the 0 here. Then I have x over square root x squared. So I have the square root of x squared is the absolute value. So I have the limit of minus x over the absolute value. So then if x is positive, if I'm coming in from the right, my absolute value is just x. So I have x over x with the minus, so I get minus 1. If x is negative, the absolute value is minus x, and I have the two minus signs and the limit of 1, so I get plus 1. So here are three choices of paths. The one where x was 0, my answer was 0. The one where y was 0 and x was positive, I got minus 1. The one where y was 0 and x was negative, I got 1. And you could go on and on and on with this. Suppose you came in on the line y equals x. So replace the y with the x, and then take your limit as x goes to 0. And you'd have, you see, your 2x squared, so absolute value of x root 2. So then, again, depending on whether x is coming into 0 from the right or the left, you'll get either a minus or get a plus. So now I've given you 5 different limits, depending on just what you did. So you can see that you don't have a limit at 0, and that's why the white patch in the graph. If you turn the page, you see that we have the same kind of thing with 42 and 43. Down here, here's 42, and you want the same kind of demonstration. So take the path where y is 0, and you have this, which in turn is 1, and then you have the limit as x goes to 0 or 1, which is 1. But if you took the path x square, y is x squared, so you have x squared square, so you have x fourth twice, so then this becomes the limit of a half, and so that's a half. So that's enough to show you're not going to get a limit at 0, 0. And of course you can play the same game and get all sorts of choices. And then last one of this sort, 43, if you wanted to demonstrate all at once how many choices you could come up with, say the path is k x squared, where k could be any number. So replace here and here, and do your algebra. You see the x fourth will factor top and bottom, and so your limit then is going to have the form 1 minus k squared over 1 plus k squared, which doesn't depend on x. So your limit would be then this formula, 1 minus k squared over 1 plus k squared, or the x fourth cancels out. And so that means you would get different answers depending on your choice of k. So if k is 0, your answer would be 1. If it's 1, it would be 0, and so on. So here, the difference between these that we've done and this one is that it doesn't have to be just at 0, 0 that you fail to be able to get a limit. So this one, you notice my xy is approaching 1, 1, where I have a 0 over 0 form. So what you're looking for in these problems, geometrically, if Maple's made the drawing, is where you get the white patch in the graph, but algebraically, it's where you get a 0 over 0 type situation. If you simply take the target numbers, which would be these numbers, and throw them into the formula. Sometimes you do get a limit, of course, but you don't always. So with this one, suppose you had the path x equal 1. So you replace that with a 1, and then you could factor here and cancel, and you'd have this limit, which is 2. Then suppose you had the path y equals x, so equally well x is y. So if you replace the x with y, you'd have y cubed. This x multiplies the y square, it doesn't multiply the minus 1. So you'd have y cubed minus 1 over y minus 1. And you could factor your difference cubes, and then cancel. And then you have the limit of y squared plus y plus 1, and that's 3. So again, you get different answers. The answers don't, but it doesn't have to be 0, 0, and your answers don't have to be zeros for this situation to apply. So then the last type of problem for today in this section is using what your book calls the sandwich theorem, and some people call it the pinching theorem, and some people call it the squeezing theorem, okay? See, this depends, I guess, on whether your main interest is food or whether your main interest is romance, right? Okay. Well, gotta laugh about something in the morning. So consider a couple of, well, 3 functions. You're going to squeeze the function f with the functions g and h. And it's the same idea as in Math 170, except now they're functions of 2 variables instead of 1 variable. So the idea again is that here now, when you're talking 2 variables, you're not working on an axis, you're working in the plane. So you think of your domain now as like a circle, centered at wherever it is you're trying to say that there is a limit. And so the x0, y0 would be, you're trying to say there's a limit at x0, y0 for the function f. And so you think of circles centered there. And if you can say that interior to these circles, the f is always between this function and that one, and then you can say that this function and that one both approach the same limit L, then this function that's always in between has to approach L also. And this is at least going to be true when the g and the h are continuous functions. If they're discontinuous, then you can get into more issues about just how they're discontinuous, but we're not going to go there. The book's assuming that they're continuous functions. If the limit then for g and for h, if they have a common limit that's a number, L, then the f will have a limit and it'll be L also. So in problem 55, we're given this inequality. Now it might be quite a bit of work to prove this inequality, but you're not asked to do that. The book's giving you that. Okay, so be grateful and don't argue. And so given that, you could call this G, and you could call that H, and then what you're trying to say is that if G and H both have a limit as x, y goes to 0, 0, then f must have that limit also. So if you look at x, y going to 0, 0, in your function g, that limit is certainly 1. 1 minus 0 over 3. And the limit of this constant is certainly 1. So therefore, having called this thing f, that limit is 1 by the sandwich theorem. Okay, that one's comparatively easy. Look at 56. So you're given this inequality, which again you aren't asked to prove, but are allowed to use. And what you're trying to do is prove a limit about 4 minus 4 cosine square root divided by the absolute value of xy. So from this inequality, first thing you do is divide by the absolute value of xy, so that you get this one, which would be true certainly as long as xy is not 0. And then you have this function squeezed between these. So the question now is, as xy goes to 0, 0, or the product goes to 0, what's this limit? Certainly this, the right-hand side, the limit of 2 is certainly 2 without any real issue. The question is, what's your limit here? Well, since you're dealing with this absolute value, you have two cases, because the product could be positive or negative, right? And so if it's positive, the absolute value is xy, and if it's negative, it's actually minus xy. So when xy is positive, you can simply write xy, and then you would have your function that I'm calling g, 2 minus x square y square over 6 xy, and so that's 2 minus xy over 6, as xy goes to 0, 0, and that's certainly 2 minus 0, which is 2. So if xy is positive, your left-hand side limit is 2, your right-hand side limit is 2, and you have 2 for this limit. You're not quite finished though, because the xy could be negative, so your absolute value then is minus xy, so then you have minus 6xy. The two minuses make a plus, but again, your limit here would be 2, because it's 2 plus 0. So either way, you can apply the squeezing theorem and then say this. So with these, if you have to deal with absolute values, you're going to have two cases where your absolute value can be plus or can be minus, whatever your variable is. Okay, so 58 is that kind of thing. This one is certainly true, isn't it? Because by definition, sine and cosine can never be more than 1 or less than minus 1, because they're the ratios of sides of the right triangle, say. So this is certainly true by what the cosine is, and this would also be a true statement if you said sine. The problem, of course, is that you don't really know what to interpret as a value for cosine of 1 over y when y is 0. So what this wants is the limit of x times cosine 1 over y as x goes to 0 and y goes to 0. So first of all, you have two cases, because x could be positive or x could be negative. So if x is positive, then you can multiply all the way across, and if you're multiplying by a positive, you don't reverse the inequalities. So you can say that. If x is negative, then you reverse the inequalities, and the value of x, the absolute value of x then would be minus x. So if your x is negative, then you have the x times the minus 1, or minus x, and you reverse the arrow, and then you'd have your x cosine 1 over y, and then here you'd have your x times 1. So your x then is less than or equal to minus x cosine is less than or equal to x. If you rewrite this, reading it from left to right, when x is negative. See, when x is negative, this is a negative number, and this over here is a positive number. So as xy goes to 0, 0, both this and that go to 0, so then you can apply your sandwich there. So what we'll talk about tomorrow now is how to do the derivative of a function of two variables. So that's called the partial derivative. And so to do a partial derivative, for example, with respect to x, as we'll see tomorrow, you pretend that y is a constant, and then use your same rules from Math 170 for doing the derivative with respect to x. But every place you see a y, you treat it the same way as if it were a 3 or a 5 or something. So it isn't really that hard to do partial derivatives, but there's more to it as far as interpreting what it means. So most of tomorrow's class will be looking at my efforts at artwork and some maple, of course, and in the direction of interpreting partial derivatives. So I'll see you tomorrow, if all goes well for us all.